Welcome back to Math 103. This is video number 8 on growth and finance. Let's shift back from population examples to financial ones. Suppose that you put $5,000 into a savings account on January 1st of 2016. On December 31st of each subsequent year, the bank will pay you 2.3% interest on whatever money has been in the account for the entire year. So we're going to start studying the notion of receiving interest on a bank account, and we're going to do that by first looking at banks that pay interest only once per year. We'll make that more realistic later on and talk about banks that pay interest more often, but for the moment, the idea is you put money in on New Year's Day, and whatever money was sitting there the entire calendar year, you receive interest on that money. You can't deposit money on December 30th and think you're going to get a year's worth of interest the next day. Your money has to have been sitting there the entire year to get a year's worth of interest. So we can ask the following questions. How much will be in the account after 1 year? How much will be in the account after 2 years if you don't withdraw any money, but leave it in the account to just sit there and grow? And how much will be in the account after 10 years if you don't withdraw any money, but leave it in the account to grow? Well, if you think about it, this is again the same math we've been doing all chapter long. Your $5,000 investment sits in the bank one whole year and grows by 2.3%. That means it's being multiplied by its growth factor, 1.023. This goes on for just 1 year, so there's only one multiplication by 1.023. If you leave this money in the bank and let it sit there for another year, then this same quantity will be multiplied again by 1.023. So the overall effect will be to grow to 5,000 times 1.023 times another 1.023. In other words, $5,000 times 1.023 squared. How about after 10 years, just leaving the money in the account to keep growing, to be multiplied every year by an extra factor of 1.023? Well, after 10 years, we'll end up with $5,000 times 1.023 to the 10th power. So this is just the same thinking we've been using all along about growth factors. Right here is the 10-year growth factor. It's the same thinking we've been doing all along, but now specifically applied to bank accounts and interest. To highlight the key idea, on December 31st of every year, the bank is looking at the current account balance at that time and multiplying whatever's in your account then by 1.023. Now, since it's multiplying the current account balance by 1.023, including all the accumulated interest that you've earned up to that time, including interest from previous years, when the bank pays you interest, you're earning interest not just on the amount you originally invested, the original $5,000, you're also earning interest on all those interest payments from all the previous years. So this power of earning interest on interest is very significant, and the interest that you earn in this situation is described as compound interest. You're not just earning interest on the original $5,000 investment, you're earning interest on all of your previous interest payments. We're on our way to finding a formula for compound interest. First, we need a little bit of terminology. The amount that an investment is currently worth is called the present value, and we'll denote that PV when we write this in formulas. The amount an investment will be worth at a specified time in the future is called the future value. We'll call that FV when we write it in formulas. An interest rate is typically quoted as a so-called annual percentage rate, or APR. That is to say, when you go into the lobby of a bank, or you look on a credit card statement, you will see a percentage that represents a year's worth of interest. In computations, we'll always convert the percentage to a decimal, and we'll denote that decimal I in the formulas. Okay, well, so we have to be clear which is the percentage and which is the decimal form. So 100 times I percent, is equivalent to I as a decimal. It's always I, the decimal form, that we'll compute with. So, for example, I realize this is a little mystifying, this notation. As an example, if you take out a loan at 6% annual interest, the APR is 6%. But I, the decimal form, is 0.06. So we're used to this idea of percentage versus decimal. The new idea is just to make clear that this letter I is always going to denote the decimal form in the formula. And now a crucial moment in your mathematical life. You know enough information right now to derive the formula for compound interest, to figure out, to reason out a formula for compound interest. Here goes. So recall our example of investing $5,000, that's what we're calling the present value, the amount initially invested, in an account which pays 2.3% annual interest. That's what we're calling the APR, annual percentage rate. After 10 years, we've already figured out the future value of the account will be $5,000 times the 10-year growth factor. So we can ask, well, what will be the future value after n years? Not necessarily 10, but any number of years. Well, all we're doing here is leaving everything else alone and replacing the number 10 with the letter n. We're just saying, however many years there are, well, that goes where the 10 went in this specific example about 10 years. Okay? The 1-year growth factor gets raised to the total number of years. We can go on and ask, what will the future value be after n years if you initially invest not $5,000 but PV dollars, however much PV is? Well, that just means that this amount, PV, is playing the role that $5,000 played in our concrete example. Okay? However much you initially invest, it gets multiplied by the 1-year growth factor n separate times. And now we can ask, what will the future value be after n years if you initially invest PV dollars, same situation as here, but now at an APR not necessarily of 2.3%, but of 100i%. Okay. Well, that means that our future value is going to be the present value times 1 plus I raised to the nth power. So the role that 0.023 played here is now being played by I, the interest rate in decimal form. So whatever the interest rate is, convert it to a decimal, 1 plus that is the 1-year growth factor. That 1-year growth factor to the nth power is the n-year growth factor, and that overall growth factor times present value tells you the future value, what your account value will be. Congratulations! We've just derived the compound interest formula. This is our cast of characters. There are 4 quantities here: future value, present value, interest rate as a decimal, and n, the number of times the interest is compounded, the number of times the growth factor is multiplied together to get an overall growth factor. Those 4 quantities are related by this equation. We have just reasoned our way up to this formula. It wasn't just handed to us. There are reasons why it makes sense, and we've just worked through those reasons. A key point here is that you're not allowed to plug numbers into a formula which you don't understand. This formula is doing nothing more than summarizing the reasoning process of successive multiplication by the growth factor 1 plus I, 1 plus interest rate, a certain number of times. This is just summarizing a reasoning process we've been going through throughout this chapter regarding growth factors. Please go on to the next video.